This video covers how the efficiency of different thermodynamic processes are modeled. The movie covers some thermodynamics of processes as well. So, let's look at modeling the efficiency of processes with mathematical modeling minds. Throughout the video, I talk about CARNOT cycle, CARNOT engine, CARNOT heat pump, the Rankine cycle, and IC engines. Under internal combustion engines, I will talk about the Brayton cycle, Otto cycle, and diesel cycle. CARNOT cycle. CARNOT cycle has two advantages over other cycles. It takes the maximum use of high temperature and low temperature reservoirs by operating at highest and lowest temperatures available for as long as possible. Further, all processes in the cycle are assumed to be reversible. With these two advantages, it is impractical to use CARNOT cycle in real process applications. The figure illustrates the PV diagram and TS diagram of a CARNOT cycle. The area inside the PV cycle represents the work done by the gas in one cycle, and the area inside the TS diagram represents the net intake of energy as heat by the gas in one cycle. From state 1 to 2, the gas undergoes isothermal expansion, absorbing heat from the hot reservoir. From state 2 to 3, adiabatic expansion. From state 3 to 4, the gas undergoes isothermal compression, rejecting heat to the cold reservoir. And from state 4 to 1, the gas undergoes adiabatic compression. CARNOT engine. CARNOT engine provides the highest thermal efficiency of any feasible engine. The energy balance for the heat engine is equal to QH, which is equal to minus QC minus WS. The heat is transferred from the hot reservoir to the heat engine, which is QH, and it is greater than 0. The engine extracts some work from this engine, which is Ws, and rejects the rest to a cold reservoir, which is Qc. Ws and Qc are both negative quantities in terms of they are the work done on the surroundings and heat rejected from the engine. Then we can apply the entropy balance for the CARNOT engine operating at steady state. Entropy generation is 0 because the engine operates reversibly. For one cycle of operation, the engine starts at an arbitrary state x and come back to that same state x. So there is no entropy change. Therefore, the entropy balance becomes 0 equals QH over TH plus QC over TC. We can convert it to the form QC over QH equal minus TC over TH. The thermal efficiency is given by work output divided by heat input. Substitute the values for them to obtain the thermal efficiency of the heat engine. The efficiency cannot be 1 unless the hot reservoir temperature becomes infinite and cold reservoir temperature becomes 0 Kelvin. But these conditions cannot be achieved in real applications. The maximum thermal efficiency we can get is about 50% with hot reservoir having around 600 Kelvin and cold reservoir having around 300 Kelvin. These are the typical values used in industrial applications. But the real power plants operate at around 30% efficiency due to inefficiencies in real processes. We can control the thermal efficiency by controlling TH and TZ. CARNOT engine. This is an illustration of a Carnot engine. Hot side is the boiler and cold side is the condenser. In the boiler, gas undergoes isothermal expansion where the phase change takes place. In the condenser, isothermal compression, which is also a phase change. In the turbine, adiabatic expansion of the gas takes place and the shaft work is generated. The pump compresses the liquid coming out from the condenser adiabatically and pump back to the boiler, which requires some work. Carnot heat pump. If we operate the Carnot cycle in reverse by putting work in instead of taking work out, it is called the Carnot heat pump. Now the heat flow is from the cold reservoir to the hot reservoir. Carnot heat pump has the highest efficiency as it requires minimum amount of work for a given transfer of heat from the cold reservoir. Heat pump is used for heating the buildings during the winter. Cold reservoir is the outdoor surroundings and hot reservoir is the inside of the building. Heat is transferred from the colder outside to the warmer inside with added work. The same thing taking place in the refrigerator and freezer. COP, or the coefficient of performance, is the ratio of work required to the heat transferred from the cold reservoir. The formula for COP is derived using energy and entropy balances. Vapor compression cycle. The heat pump, refrigerators, or freezers operate on the vapor compression cycle. That is a reverse Carnot cycle. But how this cycle operates? Work is put on the compressor and raise the temperature of the working fluid by compression. Then cool it to liquefy at high pressure in the condenser. Next, drop the pressure isentropically through a throttle to obtain a cool fluid. Finally, boil off in the evaporator at a low temperature. Rankine cycle. We will talk a little on Rankine cycle in this video. In most applications, the water is used as the working fluid. It is impractical to use Carnot cycle when the water is used because compressing a partially compressed liquid is complex than compressing a completely condensed liquid, and wet steam, which is a mixture of water and steam, damage the turbine blades by erosion due to water droplets. Due to these reasons, power plants use modified Rankine cycle. In Rankine cycle, the vapor is superheated before entering the turbine to ensure that no water droplets are available. This is done with usually a separate superheater installed after the boiler. In Carnot cycle, fluid that enters the pump is saturated. In Rankine cycle, fluid is subcooled to avoid cavitation. The figure illustrates the Rankine cycle operation in a TS diagram. State 4 is the actual output of the turbine and 4' is the output of a reversible adiabatic turbine. State 4 always lay right to 4' because real turbines generate entropy. At the exit of the turbine, steam quality is kept above 90% to avoid turbine blade damages. Internal combustion engines. Internal combustion engines use air, mixed with a small amount of fuel instead of using water as the working fluid. Combustion of the fuel provides energy to heat the gas mixture, and then the hot gas does the work as an expansion. Physical loop is not required in IC engines because of using air. The atmosphere completes the loop. Examples of IC engines are Brayton cycle, Otto cycle, and diesel cycle. Brayton cycle operates with a gas turbine and present in jet aircraft engines. Otto cycle describes the modern automobile engine. Diesel cycle is quite similar to Otto cycle except that fuel is injected after the compression. Both Otto and diesel cycles are referred to as air standard Otto cycle and air standard diesel cycle. Brayton cycle. The schematic diagram illustrates the Brayton cycle. Fuel is supplied to the combustion chamber. The produced hot gas generates shaft work at the turbine. The compressor runs from using some part of the energy from the hot gases. The efficiency of the cycle is given by the ratio of net work done divided by heat of combustion. By applying energy balance to the equipment individually, we get the efficiency equation in terms of enthalpies. If you want to see how the energy balance is applied for compressors and turbines, then refer to my video on energy balance for process equipment. Then we can substitute for enthalpy in terms of temperatures, and the Brayton cycle efficiency is given in terms of temperatures. Otto cycle. Otto cycle describes the modern automobile engine, or you can say a petrol engine or gasoline engine. It is a constant volume heat addition process. From A to B, isentropic compression. From B to C, isochoric heat addition. From C to D, isentropic expansion. And from D to A, isochoric heat rejection. The efficiency of the cycle is given by the net work divided by heat input. Net heat is given by the heat input minus heat rejected. And we get the formula for efficiency using temperatures. Diesel cycle. Diesel cycle is a constant pressure heat addition cycle. Higher compression ratios can be obtained with diesel cycle because there is no concern for pre-ignition like in Otto cycle. At first, the air is compressed and then the fuel is injected to the compressed air using a fuel injector. So, it undergoes compression ignition and combustion occurs relatively slowly. From state B to C, isobaric heat addition. From C to D, isentropic expansion. From D to A, isochoric heat rejection. And from A to B, isentropic compression. The thermal efficiency of the diesel cycle is given by W net divided by Q in. The net work is equal to QBC minus QDA. And here we use both Cp and Cv values in the efficiency formula because of constant pressure heat addition. And this is the end of this video. If you really like the video, give thumbs up and subscribe for the channel and press the bell icon for new video notifications. Thank you.